So let me pop up here what we were working on the first time out. We have a fictional company that we called ABC Plastics Company. And essentially what we did was we built a very simple network, what's known as a router on a stick. So we have three different subnets, three different parts of the business in our building, in our headquarters building, that do three different things. We have an accounting department, an engineering department, and an IT department. And so each of those departments, all of the users that we're representing with three simple PCs in this particular emulation software. This is just a network emulation software if you're not familiar with it. We're pretending we have a real switch and a real router and things like that. We're just emulating that environment. So we've got three potential users in accounting, three in engineering, and three in IT. And so what we did for our first session that we held a couple months ago was we essentially configured all of the routers and switches to do what they needed to do to provide network connectivity between these devices. So everything that you see me hovering over with my mouse right now, or that I have selected in this box, that is what we built on our first lab. We plugged everything in. I believe we actually ran our own little virtual cables and everything. We connected everything up, and we configured this router. We configured these four switches. As you can see, the three switches in each department, what I would call the departmental switches, for lack of a better term, they all connect up to what we have, what's known as an aggregation switch. No big shock. It aggregates all of the connectivity up to a single physical connection. And so for any of you who are experienced in any portion of networks, even at the simplest level at that CCNA or CCNT level, it's probably apparent to you that essentially we have one virtual local area network represented here in this accounting group, one virtual local area network represented here in the engineering group, and a third one represented here in the IT group. So each of those has a VLAN or virtual local area network number associated with it. I think we decided to make this VLAN 192 for probably pretty obvious reasons if you look at my mouse pointer. We made this one 172, and we made this one 10. And you can pick any number for those between 2 and 4096, with the exception of a handful of reserved or VLAN numbers that are off limits. So essentially what we're doing is we are taking all of these switches, which normally perform, in fact, these do perform a layer 2 function. All they ever do is switch Ethernet frames from these PCs to some other PC. We're just grouping them separately and allowing all three of those broadcast domains, those VLANs, to travel across this one physical interface, this one physical connection, up to the router. So if most of you probably recall or knew or know or were even vaguely aware, because of the business we're in, that any device on a single network, a single subnet like 192.168.0.0, any one device that wants to talk to another device on the network, say from PC1 to PC2, like I'm hovering with my mouse, simply creates the packet for whatever a piece of information is that needs to go from source to destination, and encapsulates it in IP header. So his IP address, which if I hover over him, it says it's 192.168.0.3. I would point to it with my pointer, but when I move the mouse, the little box goes away. And then it's going to send that packet over to destination address 192.168.0.4. So this PC simply encapsulates that IP packet inside of an Ethernet frame. So further encapsulation from where we started. And that frame is targeted towards, it has a source MAC address, the MAC address of the network interface card on this PC, and a destination MAC address, which would ostensibly be the MAC address on the Ethernet card on this PC. It looks like it ends in 22CB, 22 Charlie Bravo on our particular emulated network. Now, in the case where this PC1 does not know, it knows the IP address it's trying to get to, but it doesn't know the MAC address, well, Ethernet has a set of rules. It's a protocol that gives us a mechanism to figure out what that MAC address is. And essentially, it sends an ARP request, an address resolution protocol request that says, hey, somebody out there has the IP address 192.168.0.4. I need you to respond back to me and let me know what your MAC address is. I need your physical address. So that frame goes out, that ARP request frame goes out while our original piece of information we want to send gets queued up, gets set to the side, essentially. And that ARP request goes out and says, hey, everybody on my local area network, the destination MAC address for that request is all Fs, FFFF, FFFF, FFFF. So everybody on my local area network, I'm talking to you. I want you to look at this piece of information I'm sending because I need some information back from you. And it essentially asks the question, hey, who has 192.168.0.4? I need you to respond back to me. When that PC responds back, then I'm going to have that MAC address. I'm going to have that physical address on top of the local address, or excuse me, logical address that I started with, logical address being the IP address. And we can have our conversation, our communication. So that frame goes out up to this switch. And this switch sends, if you look down the VLAN column, every single interface, every single fast Ethernet interface on this switch is assigned to VLAN 192. Well, all but one of them, all but fast Ethernet 0/4. We'll talk about that in a minute. And I know I'm rehashing some of what we talked about before, but bear with me. And so it will send it out every single interface that is in that same VLAN and that same broadcast domain, because this is a broadcast frame, except the one that it came in on. So a copy goes here to PC0, a copy goes here to PC2, and a copy actually goes up here through aggregation switch and all the way up to router 0. So that interface, and that interface all look at this frame. Oh, it's destined for FFFF. That must be for me. I better open this up and look at it. They look inside, determine that it's an ARP request, and it's an ARP request specifically for whoever owns 192.168.0.4. As such, PC0, which has a different IP address, he's .2, router 0, who has the IP address of 192.168.0.1, they realize, oh, that's actually not for me. I'm not going to respond. Just going to take that and throw it in the trash. It has nothing to do with me. I'm not going to respond with, no, that's not me. I'm just simply not going to respond. Those are the rules that I play by when it comes to address resolution protocol, or ARP. But PC2, opening that envelope, realizes, oh, this is for me. And it simply responds with it, yeah, I'm the one that owns 192.168.0.4. You found me. So that response goes back. But that response is destined for the IP and MAC address of the original sender, the original source. So that response goes through this switch, and this switch knows, because it has a unicast or very specific MAC address, oh, this should go out this port right here, which if I hover over it is our fast Ethernet 0/2. We'll go out fast Ethernet 0/2, go to PC1. Now PC1 actually knows the MAC address it was originally trying to hit, and then sends that original frame out with that with the learned destination MAC address, and communication commences. That's a long, long way to say we configured all of these switches and even this router to essentially allow communication from one PC to another, and that's all we did. So up at the router, if any PC is trying to talk to a PC in some other domain, some other broadcast domain, or some other subnet, or some other VLAN, then it just has to go through the router. The rules say you got to go through the router if you want to talk to another subnet. And the IP address on the router is typically referred to as the gateway for that particular subnet, that particular local area network. So let me walk through real quick what we configured. We did it already, like I said, the last lab, but I want to walk through it here so that we can just take another look at it. And if we go to the command line interface for this switch, we can see that we named it accounting, cute name, but it goes with the department, so it's meaningful. And I just typed the enable keyword or command so that I can get myself in privilege executive mode. I can do all of the things that could be done on this switch, including any configuration commands or any important debugging commands. So if I just type show running config, I want to see what the current running configuration is on this device, and hit enter. We see where it starts to say, okay, here's everything that was configured on it, some of which came in by default on the device because it came out of the box that way, some of which we configured ourselves, customized. Like the host name, we gave it a host name. When it was born, it was just called switch. We gave it a better name than switch. And I'm going to hit the space bar to advance further down the screen. And you can see where each of the interfaces, we have called it what's known as an access interface, the intention being that a single host would be plugged into it most often. and we've assigned it to that virtual local area network, VLAN 192, that we talked about. So anything plugged in here gets sucked into this magical domain called VLAN 192. And you can see fast Ethernet 0, 2, 3, not 4, but 5, 6, and so on and so on and so on are all configured for that VLAN 192, that broadcast domain. Now, fast Ethernet 0/4 has a different configuration on it. We've configured it as a trunk interface as opposed to an access interface. So essentially, this switch is configured in such a way that any traffic headed out fast Ethernet 0/4 headed upstream towards aggregation switch is going to have a VLAN tag assigned to it, or that it's going to basically, we're going to wedge in that VLAN 192 marker to say, hey, this is a frame, this is an Ethernet frame, because we are switches and we're switching, we're not routing. This is an Ethernet frame that originated from this VLAN 192, this very specific broadcast domain. So the trunk is just simply set up to pass more than one frame, and it distinguishes them by different VLANs, if you chose to do it that way, by use of that VLAN tag that gets wedged in there. So other than that, there's really not much else configured on this thing. One of the things that should jump out at you is there's no IP addresses on this switch at all. This is a true traditional layer 2 Ethernet switch. It simply focuses on switching frames as quickly and reliably as possible. If it knows the destination address, it'll send it out that particular interface. If it doesn't, it'll send it out all the interfaces in that broadcast domain except the one from which it originated. And those are the basic rules of Ethernet for all intents and purposes. Let's see here. So what we're going to find is that the engineering switch is configured almost identically in the same exact fashion. Show running configuration, except it's VLAN 172, and there is a single trunk interface that we use, again, fast Ethernet 0/4. And it's just configured to allow tagged traffic from any virtual local area network, from any VLAN to go through. IT looks exactly the same, except it's VLAN 10 instead of show running configuration, instead of 172 or 192. Everything else is the same. So a very generic setup. This is the simplest way you can configure a switch. And if we're being technical, you don't have to configure it this way with what we built here. But because we have an eye towards the future and the eye towards the fact that we're having 3 different local area networks that we wanted to intentionally separate with separate subnets and separate broadcast domains, we went ahead and built it that way. Before I go take a look at the configuration for the aggregation switch, does anybody have any questions at this point? Is there anything specific that you want me to double back on or that's confusing we should talk about? Or is it so far hopefully at least making some degree of sense? I'm going to try and move this out of the way if possible. Wish I could see all the attendees at once. There we go. Now I can see everybody at once. So I'm going to assume that silence means you understand and you don't have anything to say and you don't have any questions, because nobody's unmuting, and I believe I gave you the power to unmute. So let's move on to aggregation switch. Enable, so I can do all the fun stuff. Show running configuration. Let's just look how this is set up. We decided to call it ag switch. And we have, I'm going to go through this line by line with the enter key. We've got 4 interfaces that are actually doing stuff, all of which are set up as trunk interfaces. We intend to have tagged traffic across these interfaces. So what you'll notice, I'll move this off to the side but leave it on top. What you'll notice is all of our VLAN 192 traffic comes in this way on this interface, which just so happens to be fast Ethernet 0/1. There you go. This will have all the VLAN 172 traffic. That happens to be interface. It's hard for it to show up. Oh, my mouse is taking over. You can do it. I know you can do it. It's supposed to pop up on the screen. I'm going to make it happen. All right, I'll just do this. There you go. Fast Ethernet 0/2. Apologies. And then for IT, it's fast Ethernet 0/3. So we know that 0/1 is going to handle all of the VLAN 192 traffic. We know that 2 is going to handle all the VLAN 172 traffic, and 3 is going to handle all the VLAN 10 traffic. And again, we can safely assume that anything that originates on those VLANs originates from those IP networks as well. So fast Ethernet 0/4, that should be this one. Let's see if I'm right. It is. Fast Ethernet 0/4 connects to fast Ethernet 0/0 on router 0. This one's also set up as a trunk, but could potentially have all of these VLANs, any one of these VLANs on it. And again, the way that traffic is distinguished, how do I know which VLAN it's supposed to be coming from or going to? It's going to have that VLAN tag in there. In fact, let me pull up my drawing tool for any of you who are not familiar with the structure of these packets. Let's untop this one. And let me make sure this is working the way I want it to work. I like to draw pictures. I think it's easier to explain with pictures. It's really fuzzy without pictures. So I got my paintbrush. So it's going to be very sloppy. You have been warned. So if this is our Ethernet frame, we know we're going to have some kind of payload, some kind of information we're trying to send from one computer to another, like hi. And we know we're going to have, among other things, we're going to have a layer 4 header. So it's going to be talking about TCP or UDP ports, things like that typically. We're going to have a layer 3 header. I want to put the 3 up here, which is going to have IP addresses, both a source and a destination. And we're going to have a layer 2 header, 2, which is going to have a destination MAC. Oh, that's very sloppy. My apologies. And a source MAC. I'm still learning to use this drawing pad. That way here at the end, you're going to have something that's an Ethernet footer that has something to do with checking the integrity of the frame, make sure nothing got corrupted on the way. With all those ones and zeros, sometimes they get mixed up. If they get jumbled or mixed up, then the frame's no good. It gets thrown in the trash. So what we're doing in the case of, go back to my other piece here, in the case of anything that has to be tagged as it enters these interfaces, these trunks headed upstream or downstream or whatever, is we basically jam up inside here a VLAN tag. So it could be VLAN 192, could be 172, could be 10. But we basically just wedge it right in here among some other information. The piece you care the most about is a VLAN tag. And that's how it knows, oh, this is for VLAN 10. This is only for VLAN 10. We got to remember that. So essentially, all of those can come up to the router. Anytime traffic from VLAN 192 needs to speak to VLAN 10, for example, it's going to get switched here, get switched here, get switched here. The router is going to look at it and go, oh, that's destined for this other subnet. So I'm going to take off that VLAN tag I started with and put this new one on and pass it on through, but it's tagged for this VLAN, so it's going to go this way. And the same exact functionality we talked about in learning MAC addresses happens in this whole architecture overall. Every one of these devices has a table that ties all the MAC addresses to a physical interface that it learns. Let's see if aggregation has a good list of MAC addresses we can look at. Show MAC address table. Yep, already got a bunch of good stuff on there. There's a chatter amongst these different VLANs. There's 10, 172, and 192. We've learned some MAC addresses. So any traffic destined for this MAC address is going to head out this interface, fast Ethernet 0/4, which I believe heads towards the router. I think that must have to do with the router communication. These VLAN 1 addresses, we're going to ignore them for the time being. Basically, there's some untagged traffic that actually crosses your trunks. It's typically used for what we consider control plane activity. It's for the things that the switches and routers are doing behind the scenes and talking to each other to coordinate and make sure they understand and know what each other is supposed to do and all of those fun things. I won't go into a ton of detail on that right now. So, and we can do the same thing. We can look at any one of these switches and their MAC address table, show MAC address table, and we've learned one whole MAC just from something upstream. So if I were to, for example, let me put this here. Maybe I'm just going to do PC8. What if I try to ping something? Ping. Let's pick an address that's up at the router. So 192.168.0.1 is up at the router. And the reason I know that is if I hover over the router, you can see it right there. Fast Ethernet 0/0.192. I'll explain that specific nomenclature here in a second. I'm going to ping it. I'm getting a response. Happy times. If I look at the MAC address table now on IT, I have learned a couple of MAC addresses since then. Very cool. So specifically, ipconfig/all, the MAC address of this PC ends in Bravo Delta 4 Delta. And if you look at the MAC address table, it looks like that device is plugged into VLAN 10 on our fast Ethernet 0/3 on our switch, which appears to be right. There you go. So that's how they keep up. That's how they make sure to keep track of what frames are supposed to go where. Again, you notice no IP addresses here. Ethernet switches essentially function like our cable modems typically, not always, but typically function. They keep up with MAC addresses. They know which way MAC addresses are. If somebody's trying to send something to that MAC address, they know to send it that way, to the right, to the left, to up, to down, out a specific interface. That's essentially what our cable modems are doing, despite the fact that we often access cable modems through an IP address. The base function from the perspective of the customer, most often, is as a layer 2 bridge. It's got an up and a down, or a left and a right, and that's all it has, and it just pays attention to MAC addresses, sends a frame the right direction based on what it knows. So, all right, so let's see. I think that kind of covers what we configured. The only thing is, we'll just jump into the router real fast. So in the router, we have, and we didn't give it a name, anything better than router, which is what it is coming out of the box. That was a little lazy of us. We could have called it HQ router. Let's do that real quick. Let's say configure terminal. Now I'm in global configuration mode, and you can tell because my prompt changed. And let's just say hostname HQ router. Much more dignified. Great. So I'm going to get out of configuration mode and back into just privileged executive mode where I can look at the configuration. Make this a little wider. And let's do a show running configuration. And let's walk through this real quick. All right. So our router is doing a number of things. I'm going to skip this section and come back to it. First and foremost, our router is playing the role of IP gateway for VLAN 10. The reason that we know it is doing so is because the configuration on our fast Ethernet 0/0, that physical interface, has a sub interface with a .10. And inside the configuration specific to that sub interface, and you can tell it's specific to the sub interface because it's indented like this, it says, hey, we're going to encapsulate or decapsulate traffic for VLAN 10. Anything that comes into this physical interface marked as a 10, just like this, if it comes into my physical interface headed for some IP source and destination, some MAC address source and destination, anything that comes in, we're going to treat it in a certain way. My interface that participates in that broadcast domain, it's got this IP on it, 10.0.0.1. And then we've got another interface that does the same distinguishing, that same tag. That's what we call a .1Q tag. So the Ethernet, or excuse me, the IEEE protocol, traditionally the IEEE protocol for over here for Ethernet is known as 802.1, not for Ethernet, but for tagged traffic. 802.1Q. So it's very common to refer to the tags as a .1Q tag, or VLAN tag is often commonly what it's referred to as. So it depends on the manufacturer. We happen to be using Cisco's emulation tool with Cisco emulated routers and switches. Other manufacturers have other ways they reference it, but the principle is still the same. There's still a tag wedged in here. And it's either considered tagged traffic or untagged traffic in some form or fashion. So we're saying, hey, use the encapsulation, the Ethernet encapsulation method known as .1Q. And that's why you see that in that configuration right there. And again, my interface that participates in that broadcast domain happens to have this IP address on it. We got another flavor on the same physical interface, fast Ethernet 0/0. Trying to highlight that just for you right there. Another sub interface, this is anything tagged like this, comes into this layer 3 interface. So that's how the router is able to route traffic between different VLANs. So going back to the basics of how networking works, switches switch Ethernet frames through their respective broadcast domains, and routers actually route IP packets between different broadcast domains. So we built it in a way that instead of having 3 cables that run into this router, 1, 2, 3, we just aggregated them all together into this aggregation switch and used VLAN tagging to distinguish between the networks. Could have done it another way. This is just the way we chose to do it. Not an uncommon way to do it because some routers don't have 3 interfaces available on them. If we look at the physical configuration on our router, let me try to zoom in here, make it a little better. You can see we've got 1, 2 interfaces. There's only 2 Ethernet interfaces. I know it's really tiny, but you'll have to take my word for it. Fast Ethernet 0/0 and Fast Ethernet 1/0. Yeah, I believe that's on there. And these others are not actually network interfaces. They're auxiliary or out-of-band management or console connections. It's for managing the device itself. They don't play the role of the routing things that this router does. And you can see there are some expansion slots here. This is slot 1, this is slot 0. You can add some different flavors of cards into this box. But the way our device is, the one that we bought out of the box, it is a, what is this anyway? I don't even know what model this is. Ah, it's a Cisco 1841. So this particular model we bought for our fictional company, show version, is a Cisco 1841 with lots of cool software running on it. So I just type the command show version and I get a lot of that detail. All right, so that really wraps up everything we covered, and I know it's a solid 30 minutes on it, but I think it was important because there was such a gap and because so many of the folks that are on the call now weren't on the call before. I wanted to, let's see what's in the question pane. I wanted to cover that. Can you unmute yourself, Justin? It's going to be so much easier. I can't read the question because it all runs together. I cannot read this. I don't like this interface so much.
Transport VLANs? And what's that do to the frame?
Ask it one more time. I lost the front end of what you said.
Can you explain double tagging or transport VLANs? When are they typically used? And what does that do to the frame?
Oh, that's a great question. Okay, so it depends on the implementation and it depends on the use case. So and it's not surprising to a question like that because so many of us, if not all of us on this call, live or have lived in a service provider type of environment. So let me preface the answer by saying this thing that we're building here, this little thing, is very much more like, again, small business, small to medium business, or enterprise class devices and configuration style. And it's very much about we're one company, we're just simply our own single organization, and our job is we don't provide network services per se. We do whatever the accounting department and engineering department, IT department does. This is ABC Plastics, right? So we make plastics or something like that. So it's very much internal connectivity. It's very much about, this is just the people that work at the company that plug in and do their thing. Now your question, Justin, is very much geared towards what's considered the service provider side of the universe. So let me clear my screen off here. Essentially, we're talking about, hey, I've got this network, and the purpose of my network, here's a bunch of routers, and maybe these could be switches too, especially with respect to Justin's question. And what we do, what our company does is we provide network connectivity of some kind. Could be Ethernet, or excuse me, could be internet, could be maybe point-to-point connectivity, at least line circuits, things like that. But basically what we do is we provide a connectivity solution to some company just like ABC Plastics. So if ABC Plastics has their network, this network right here that we've just been staring at, so let's say that's our router, that's our aggregation switch, there's our 3 departmental switches. I know it's ugly, so bear with my terrible drawing. And we plug in and say, hey, I need to get from here to some other location. I've got an office in Tulsa, and I got a whole other network with a bunch of stuff off of it. I'll draw cloud because network engineers love to draw clouds to represent stuff. That's what we're really good at. And so I need you to get my traffic from here to there. And maybe for some reason I choose to tag that traffic. I got a .1Q tag on my traffic headed this way. And I want it to be tagged across this environment. I want you to preserve my tag. I don't want you to pay attention to it. I don't want you to do anything special, but make sure my tag is there when the traffic spits out on the other side. I need you to preserve that tag. So the original implementation that we had long before the Metro Ethernet Forum existed or came out with all of the fancy Metro Ethernet circuits that we very often talk about today from a service provider perspective, like EPL. Oh my gosh, the handwriting's terrible. EVPL, E-line, E-LAN, even VPLS. That's terrible. Before those terms came out, the way we solved that problem for a customer who said, hey, I'll pay you money for a circuit, but by golly, you better preserve and my VLAN tag, is we essentially created a queue in queue implementation. I bet you can guess where the queue comes from. It's a .1Q tag inside of a .1Q tag. So for that same Ethernet frame we drew, let's say it originates from this PC over here. It looks more like a laptop, a happy laptop. If that frame originates here, it starts off with a destination MAC and a source, that's an S, source MAC, and other stuff, the payload of the Ethernet packet, plus his little footer. It starts off like that. It arrives on the switch, and as soon as it decides, oh, this must be sent up this trunk, I wedge in that first .1Q tag. So here's the first .1Q. I'm going to use Q. It could be VLAN 10, it could be VLAN 1000, it could be whatever we decide it needs to be. And it gets switched over here. Remember, these are Ethernet switches, so they switch them. It arrives at the router. Let's pretend this is a switch, because for the sake of this conversation and Justin's questions, this kind of has to be a switch. It still has that VLAN, let's say it's VLAN 10. I'm just going to do 10 because it was convenient. It's still got that tag. It gets sent into the magical service provider network. Inside the service provider network, another tag, a double tag, gets put on top of it. It's a .1Q tag that follows the same format and function as the first one. It sort of stacks on top of it. It's wedged in there, and it says, "Hey, this is the ABC Plastics VLAN. This is the traffic that anywhere on our service provider network where traffic flows is specific to that customer, and nobody else's traffic on any other VLAN can ever intermingle or interact with the ABC Plastics VLAN. It's very specific to ABC Plastics. So blue and red don't intermingle, green and red don't intermingle. They're separate even though they cross the same devices. That's the magic of these cool networks that we built. So our VLAN 10 traffic goes across this red VLAN or whatever number. Could be the same exact number, could be a different number, doesn't matter. They're essentially, one is transparent to the other. We can't even tell they ever put a VLAN tag, because by the time it spits out over here, the red tag gets stripped off. Let's see if I can be fancy and erase the red tag. Not pretty, but you get the picture, I hope. So the red tag gets stripped off, and now only our original VLAN 10 tag, oh, wrong color, that won't work. Sorry. VLAN 10 tag gets sent down to the network, and this thing knows, oh, it's a VLAN 10. I'm supposed to do this with it and not this, or whatever needs to happen. So that original implementation was what was referred to as Q and Q. We encapsulated our .1Q tag inside of another .1Q tag, like I had drawn here momentarily. The new implementations work the same in principle, these Metro Ethernet implementations. The difference being that they have a much more modular and dynamic means of separating and tagging and marking traffic. The principle is essentially the same. We have some mechanism that says, hey, this traffic is specific to this customer and not other customers, and leave this tag alone inside. Don't do anything to it. Don't strip it. Don't get it off there, but don't do anything to pay attention to it. Just let it pass through transparently. In some cases, you can't do it that way. In some cases, you have to do something special because you have a specific type of network you built for your customer, or they have a specific request on what should happen. Typically, though, you want to let it pass through transparently. And it just depends. If the customer has a router plugged in here instead of a switch, I know this drawing is getting really ugly. If these are routers, they're probably not going to be passing tagged traffic through. So we don't have to do anything special. We, as the service provider, put our little ABC Plastics tag, but we can ignore everything else and just pass it through transparently. So it just depends on what gets built from a service provider perspective. I know that was a lot. Does that basically answer the question you asked? The transport VLAN being the one that the service provider tacks on top of that. Does that kind of cover it, Justin?
Yes, sir. Thank you.
Absolutely. I'm going to say we answered it. I think I did this right. Okay. I think I'm making the toys work the way the toys are supposed to work. Why is this question mark still there? I answered it, by golly. Oh, there you go. Answer. Yep. Answered. I'm obsessed with the tool, and I know I'm being silly. Okay. Okay. Victory. All right, so let's go back to it. So we're about 40-ish minutes into this, and I think we've covered some good ground. I think we set the foundation of what happened before, and we answered at least one question about what's happened since. Let me make sure I don't lose any of you in terms of the screen. I want to be able to see you. Okay, cool. So now in part two, we've got this network up and running that we built. Remember I said this is what we built the first pass. You notice I left this out. Well, if you look up here, it's probably tiny on your screen. It says ISP. Oops, sorry. Internet Service Provider. So the instructions, well, each of these little modules that I built come with instructions. I'll just quickly read through them to you. Hey, you've been tasked, because we're the administrators of this network. We are the high-powered, high-paid network engineers. You've been tasked with acquiring an internet connection for this headquarters. Budget constraints have forced you to go with a cheap residential connection. Not the first time that's ever happened at a small company. And everybody on this phone probably knows that. As well, the ISP will host the company's website, www.abcplastics.com. Your ISP has decreed that this connection will be dynamic in nature. And most of you here should know what that means. Most of our internet customers that we sell service to have a dynamic in nature internet connection. They plug in, and at that time when they plug in, they get an IP. They could plug their computer in their own wireless router. I don't know, anything you can think of that gets an IP address, and it will dynamically grab that IP. So we don't know what IP we're going to get. We just need to configure it to dynamically request and accept an IP address from the internet service provider. Could be Madison Communications, it could be Charter, Spectrum, it could be Comcast, it could be AT&T, Verizon, doesn't matter. We already have a set of rules set up that say this is how we do these dynamic internet connections. Plug it in and it's supposed to work magic. So we're only going to have one usable IP address router. It's going to be the second half of a /30 subnet. I'm not going to go into subnetting here. Anybody that doesn't understand or have a good grasp on subnetting is more than welcome to pop a question in here, and we can kind of have a chat on the side, or I can point you to some good resources. Don't mind doing that at all. It's almost its own field of study. So depending on how much exposure this group has had, some of you will know it instinctively, and some of you may be really fuzzy, and I don't want to drag down the limited time we have specifically going into it. But basically what that means is there are only two addresses available in this entire subnet, where these /24s down here are much, much bigger. They've got 250 some odd addresses available to be used on host devices like PCs. So let's see here. They've also told us, hey, the DNS server that we have as an internet service provider is 68.188.0.2. You need to point your devices to this IP address if you want to do DNS. So if you have a website or something like a website, a URL, a host name, and you need to translate it from www.abcplastics.com to whatever that IP address is that's supposed to be unique in the internet world, well, then you got to send that DNS request, that domain name service request, to get that translation. You got to send it to this IP address that lives inside our magical network, our magical cloud. So first step for us is to, sorry, the mouse just jumps and does its own scrolling all the time. I apologize. The first instructions say set up the ISP facing interface to acquire its IP address dynamically. So this interface right here, where we've got our cable plugged into the ISP, to the cable modem, to the DSL router, to the, could be anything, could be a fiber-based thing, although it's a cheap residential connection, so I bet it's not fiber-based unless you're one of those forward-thinking companies. And plug it in to make sure it does the dynamic thing. Well, if I hover over this interface, I can see that it's fast Ethernet 0/1, the only other Ethernet interface on this router. Remember, we looked at the front of this router a few minutes ago, and yeah, we just got the two. So one's going south and one's going north. Easy enough. Next, we're supposed to configure a default route to the internet on the router, pointing towards the ISP's customer-facing IP address. Well, we're going to dynamically get the second half of a /30. That means the first half, or the other available address, we'll have to statically configure it. which is a little bit odd because typically in a dynamic connection, you don't have to do that. You're offered your default gateway or the other IP address that we need. So I don't know why I built the lab this way. There was a specific reason for it. I just don't remember what it is. For all I know, it's not even going to work that way. We're going to find out. Additionally, the hosts on the LANs don't have a DNS server in their DHCP configuration. It's easy to tell. If I hover over any one of these, you'll notice that it says DNS server not set near the bottom of that rectangle. So I got an IP address, I got a gateway, but I don't have a DNS server. I don't know how to do domain name service. I don't know how to do resolution for web addresses. Same with PC7. It's not supposed to have DNS. That's a mistake. That's not supposed to have DNS. That's a mistake. So yeah, my lab isn't properly configured. That's okay. We're still going to go through the experience for you anyway. I have a feeling somebody tinkered with my lab when I wasn't looking. So we've got to make sure that we are giving in our DHCP for all of our LAN hosts, we got to make sure we're giving them that DNS address so that it works properly. And then we're going to have to configure NAT, network address translation on the router, to allow the hosts on the private internal network access to the public internet. So if you think about it, we've got 9 PCs representing 50 for all we know in our fictional company that all need to go out a single interface to the internet, and that single interface has one IP address. So if we don't specifically configure this to do network address translation, your home routers, your home devices typically do that automatically by default. They're built that way under the assumption that you need them. Well, then we'll never be able to get this traffic out to the internet. The internet is never going to accept an IP packet that's sourced from IP address 10.0.0.2, for example. It'll never accept it. Internet has an agreement that any 192.168 and 172.16 through 172.31 and 10 dot addresses will never be allowed to be accepted out on the public part of the internet. We kept those to behave as private addresses. So if we don't do this translation so that it looks like it's coming from whatever this public address is we're going to get on this interface I'm hovering over, nobody's going to be able to communicate with the internet, and there's no point in having an internet circuit. So we have to bear that in mind, and we have to configure for that. And then finally, when we're done, we need to test the configuration by successfully attempting to access this website, www.abcplastics.com, from at least one of the PCs per each LAN segment. So let's jump in. Unless anybody has a question specific this second, let's jump in, because we're going to have just enough time probably to get through the tasks that they've given us, and that'll probably be everything we have for today. All right. Silence is the implicit agreement that we should press on. So we're not going to need to configure the switches at all. We shouldn't need to configure the PCs at all. They're already supposed to be dynamically grabbing IPs. We just need to configure the router. Sorry, the screen jumped again. So let's get into configure this router. I'm going to go a little bit bigger on my screen this time so we can see a little better. All right. Our router is here. Let me do a show running configuration again and make sure that nothing is configured incorrectly, because I noticed those PCs were set up in a way that made it look that way, and it looks like the router's configured properly. I don't know why these PCs are doing that. So let's do this. Let me reboot everything. And yeah, we haven't configured anything. I'm going to reboot everything and see if that doesn't clean up the stuff that is not supposed to be there. Again, I know I showed you a few seconds ago, these guys had DNS. They're not supposed to have DNS addresses. I'm going to hit the fast forward button to hurry up and get everything green again. Okay, cool. Hover, DNS not set, still on there. I must have statically configured these. Fast Ethernet, nope, global. No, I didn't. Yeah, I don't know why those, I do not know why these PCs are showing a DNS server. They shouldn't. We're going to have to pretend. This one doesn't, so that's our best use case, right? That's our best test case, PC8. So I apologize for that. So back into router 0. Let's put it on top this time so it doesn't just go away on us. Let's see. Enable. All right, so I rebooted it. Let's put that host name back where we had it. HQ router. A little dignity, please. All right, so let us start with step 1, which is set up the ISP facing interface to acquire its IP address dynamically. Does anybody on the call feel comfortable telling me what we need to configure here? If you don't, that's fine. I'll do it for you. I'd love to hear from my audience. Anybody that wants to speak up and tell me what I should type. Otherwise, I'll type it and you hopefully take good notes. And yes, I will win the staring contest. I can stare at this camera all day long. Ask anybody who's seen me present. Anyone? What should I type? What should I configure? Anyone? Anyone? I bet Jessica's laughing on the side right now. This dude is crazy. What is wrong with him? Okay, you win. Only about half of you are showing attentive anyway, so that's okay. So we are going to configure again. Recall that we are plugged into the internet on fast Ethernet 0/1. So I'm going to say, hey, I want to configure interface fast Ethernet 0/1. That's the one I'm interested in. If I do a show running configuration right now, we can see that fast Ethernet 0/1 doesn't have any real configuration on it. There's no IP address. It's just automatically set to do speed and duplex, which are physical interface configuration settings. We won't talk about those here, but basically this is about as generic as your interface can be, kind of out of the box. Doesn't know anything, doesn't do anything. So let's look at here what we see. Configure here. So I am in interface configuration mode. That's why it says config-if instead of global configuration mode, which is when the prompt says config. So any commands I type are going to be indented. They're going to be specific to that interface. So we are trying to configure the IP address of interface fast Ethernet 0/1. And so if I use the question mark, I get some context sensitive help. It says, hey, you can tell me what IP address you want to use on this interface, or you can set it to negotiate, to request an IP address via DHCP. Well, we know we're supposed to be doing it dynamically. DHCP stands for Dynamic Host Configuration Protocol. I think we know what we need to type, DHCP. And if I hit question mark, you'll notice there's nothing else in terms of options. It says at this point, you can use carriage return. You can press enter because there's no other keywords or options to specify. So I'm going to hit enter. And when I say it, man, within seconds, we have a message, a syslog message that says, hey, we were assigned an IP address of 24.217.0.102. And our subnet mask is 255.255.255.252, which some of you might recognize as the /30. This is just shorthand notation for that. Basically, that's saying, hey, there are 2 available addresses in this subnet to go on to host or router interfaces. And something called router 0 gave us that IP address. We don't care. It's out on the internet. It's an internet service provider device. We're not that particularly configured for it. So I'm going to type N to get out of my configuration mode altogether, back to regular privileged exec mode. And I'm going to type show IP interface brief. I want a brief snapshot of all the IP interfaces on this router. When I do, I'll note that fast Ethernet 0/0 doesn't have an IP, but his sub interfaces that we looked at earlier each have their own IP address based on the subnet we intended them to live in. We manually configured those IPs to do that. We did that ourselves. That's why it says it's stored in NVRAM, because it stored those IPs and remembers them because what we told it to do. And those interfaces are actually up and up. But note fast Ethernet 0/1, check it out. It's that 24.217.0.102 address. This is that public address. This is the address that the entire internet can talk to should we want to allow it. And it says the method by which it had that address was DHCP. And it's up and it's up. Everything's plugged in happy times. So that's a really good sign. So if we were to do some subnet math, we should be able to figure out that the other available IP address in this subnet is the .101 IP. So .100 would be considered the network address because it's a /30. .101 is one usable IP address, the first usable. .102 is the second or last usable address in this subnet. It's the one they gave us. Thank you very much. And .103 would be considered the broadcast address. So we know ahead of time, because of our knowledge of IP subnetting and networks, that .101 has to be the address of our router on the internet side, the service provider's router. So first thing I'm going to do as a network engineer, see if I can ping that other IP. I believe I should be able to, but let's test it real quick. Can I get to the internet? The edge of the internet is this 101 theoretically. Let's try it, 0.101. Can I ping it? It's going to send 5 packets. The first one failed. First one timed out, but 4 went through. Does anybody have a guess as to why the first one failed? Why did the first ping not make it through? There's at least 5 of you on this call that know the answer to this question because we've had this conversation before. And we talked about it near the beginning of this presentation, as a matter of fact. Any thoughts? No? It's okay. Address resolution protocol. The first time out, that first ping basically timed out because it had to be set aside while our router asked anybody else on this broadcast domain, hey, who belongs to 24.217.0.101? Whoever has that IP, I need you to respond back so that I know your MAC address. Well, the first one got the MAC figured out. The rest went through once the MAC was figured out. So if I do a show IP ARP, address resolution protocol, I can look at the ARP table on my router. Just like PCs have an ARP table, routers have ARP tables too. And look at that. I've got my IP address that I know and my MAC address that goes with it. And I've got the ISP's IP address and the MAC address that goes with it. So learning this piece of information and how it ties to this is why we lost our first ping. Everything else worked successfully. So we're pinging the internet. We're just pinging right there at the ragged edge of the internet, just where the internet starts from our perspective, but we're pinging the internet. Pretty darn cool. Well, another great test we can do is, can I hit this DNS server that lives on some other network out there on the internet? Could be 1 hop away, 10 hops away, 1,000 hops away. We don't know. But can I ping it? Let's test it real quick and see. Ping 68.188.0.2. Let's see. Nothing happening. Nothing happening. I don't know. It's not looking good. Yep, for whatever reason, we can't seem to ping it. I wonder why that is. Let's think about this for a minute. When you have to ping something that does not live on your network. See, this first ping, that lived on our subnet that we live on, our fast Ethernet 0/1. When you got to ping something that's not on your network, you can't send it directly to that. Networks have to be separated by routers. So there's at least one router in between us and this 68.188 network. Don't know what it is. Well, we don't know where to send traffic when we're supposed to be sending it to something not on our network. And that really comes, the next piece of configuration is where it comes in. You got to have a default router, a default gateway, so that it knows everything that doesn't live on my subnet or doesn't live on a route that I know, on a subnet that I know about. It needs to go this way. It's the gateway of last resort. It's the where do we send traffic when we don't know where to send traffic. So for a router, I can do a show IP route to look at the routing table. We've talked about MAC address table. We talked about ARP table and looked at those. Now let's look at a routing table. MAC address table for a switch is its global knowledge information base. It's what it knows about the universe. It knows a bunch of addresses. Traffic go this way, that way, the other way. Routing table for a router is the same thing. It knows about lots of different prefixes or subnets or networks, depending on how you define it. So if I say show IP route, let's see, I got a question from, Jeremy's already ahead of me by 2 minutes. So good. Excellent, Jeremy. He's just basically saying, hey, we don't have a route. We don't know where to send it. Exactly right. So if I do a show IP route, here's what I know. What I know is that directly connected to me, see how it has a C for connected, is this 10 dot network. And directly connected to me is this 24 dot network. And directly connected to me is this 172 network. And directly connected to me is 192.168 network. But what you don't see is a 68.188 network. We don't know what it is. We don't know anything about it. So this router is basically going to give up and say, I can't help you trying to get this packet where you want it to go. Sorry, dude. Well, you'll notice gateway of last resort is not set, and that's what this was talking about. Let's figure out a way to put a default route. If I don't know where to send it this direction. Well, first question, if we don't know where to send it, do this with the question answer piece just because it makes me happy. I don't need to, I'm obsessed with doing it. Okay, cool, sorry. I know that's a weird message, I apologize. If we don't know where to send it, which way would we send it? Does anybody have an idea? If I don't know where to send it, should I send it down this way towards one of these subnets, or where should we send it? Guesses, thoughts? Nobody speaking up. If we don't know where, here's Jeremy. Jeremy, did you want to go ahead and speak up? Oh, you unmuted for a second. I saw you do it. You can't fool me. So there you go.
Sorry, I was afraid I was going to get feedback.
That's a little bit, but go ahead anyway. It's not hurting anything.
I was going to say you have to send it out
Yeah, got to send it out to the internet. It's the rest of the world. Here in this little network here that we own and we configured before, it's a dead end. There's nothing past this network. So there's no reason to send anything that way. The only thing that lives this way from the router's perspective is the 192 network, the 172 network, and the 10 network. Everything else, send it towards the internet. Let's hope the internet does its job and gets the packet where we want it to go, and hopefully we get a response. So let's figure out a way to do that. So for the router, again, we have to configure a default route or a gateway of last resort. So I'm going to say configure terminal, whoops, and I'm going to say IP, because this is about IP packets and IP routing. IP route, I want to create a route. I'm going to manually configure a route on this device. First, they say, okay, what route? Where would this traffic be headed? And because we're trying to talk about all the traffic that's not one of these directly connected subnets, we need a way to say everything. Everything of IP universe. Well, the way you do that is instead of specific numbers like 68.188 or 24.217 or 192.168, we just say 0.0.0.0. And then the next thing it wants to know is, well, what's the subnet? What's the size of the subnet? Is it a /24? Is it a /30? It's also known as a prefix mask, basically saying how long is the network portion of that address. Well, when we're still trying to say everything, anything, geez, we don't know, 0000 is the proper syntax. So anything headed to network 0000 /0000 or /0, however you'd like to say it. Okay, great. Which way do you want to send it? You want to send it to a specific IP address? You want to send it to a specific Ethernet or fast Ethernet or gigabit Ethernet interface? You can send it anywhere you want. You can even send it to null and throw it in the trash. Well, for us, we want to send it towards the internet. So let's send it towards the IP address of the internet service provider, which we identified to be the 101 address a little earlier on, which we can ping, which is super awesome. So let's send it that direction. Hey, any traffic headed to anywhere that I don't know about, that's what the zeros mean, send it to 24.217.0.101. And let's see if the internet will do the job for us. So now we've configured that. I'm going to end out of global configuration mode. And let's do that show IP route command again. I just use the up arrow like you can do on a Windows device to get to previous commands. When I do a show IP route, interesting, we have this S for all zeros /0 pointed towards 24.217.0.101, and it has a little asterisk next to it. Well, S means it's statically configured. It means I manually configured that route in their routing table. And the star means it is a candidate to be our default route. And in fact, it won the battle of being default route because it has no competition. And said, yep, anything headed to, I don't know, send it to this IP. That's the next hop address. Now, we could have selected this fast Ethernet 0/1 and it would work just fine. But common convention and best practice is to use the IP address, because sometimes IPs move around or things change or you plug or unplug an interface or who knows what happens. And you want to make sure that your default gateway follows that IP, assuming that IP is the one you should be pointing towards. So best practice is to use the IP address. We totally could have specified fast Ethernet 0/1 if we wanted to. No rule says we can't. But now we have a way to send traffic when we don't know where to send traffic. So let's try to ping that 68.188.0.2 address again. It's unknown. It's not in our routing table. You can see it's not. So it's going to try and use that default route by the rules of IP routing. And let's see what happens. And success. We immediately are able to ping that remote destination somewhere out on the internet, somewhere in this magical cloud I'm hovering over. We are immediately able to ping it because we added a default gateway, which means the rest of the internet must also know how to get back to this /30 that lives between these two spots. Very cool. So now traffic gets to the internet. We even get a response back. We know that's true because we got the successful ping. Didn't just go out, it successfully came back. So we've accomplished two of the goals that were set up for us for the lab. Now, the question is, how do we do step 3? The hosts on the LANs don't have a DNS server in their DHCP information. Again, I'm going to hover over PC8 as our good example. DNS server, not set. Now, where did PC8 get its IP address from? It got it from, let's go to PC8. I'm going to put it on top here for convenience sake. I like to have my drawing always handy on the left-hand side or somewhere on the screen to refer to. I'm a very visual learner. I like the pictures. If you can't draw me a picture of it, you probably can't explain it. You probably don't understand it. So for me, the visual is like, I can't live without it. Even though I don't need it, especially a network as simple as this, I prefer to have it. So let's look at our configuration for PC8. Let's see, we're set to DHCP. We're set to dynamically learn it, and we've dynamically been assigned 10.0.0.2, which is a /24, also written as 255.255.255.0. Excuse me. We learned that our default gateway is 10.0.0.1, which you'll recall actually sits on our router. Show IP interface brief. There it is. So hey, if you're trying to send traffic to anything not in the 10.network PC8, send it towards the MAC address that belongs to 10.0.0.1. And then you'll notice also grayed out is the DNS server, and it's grayed out because it's been dynamically configured. There's nothing there. So whoever told us that our IP address is this, that our subnet mask is this, and that our default gateway is this, they didn't tell us anything about DNS. Some of you probably recall when we scrolled through the configuration, show running config, there's some stuff we said we're going to come back to. Well, there's the stuff. Close that. There is a DHCP pool called accounting. There's one called engineering, and there's one called IT. And inside the configuration for each of those pools, you notice the indentation specific to that pool. It says, hey, any host that want an IP address, give them one out of this network, 192.168.0.0, and tell them to use .1 as the default router. Tell them to use me if they live in that VLAN. This is the IP you can have. This is the subnet you can have. If they live in this pool, engineering, assign them an address out of this group, this /24, and tell them their default router is that. If they live in IT, give them an IP from the 10 dot and tell them their default router is that, which is precisely where PC8 is hanging out. So I'm going to hit Control-C to stop scrolling through the configuration and type show IP DHCP binding. I believe that's the one I want. And you'll notice we have a list of 9 IP addresses, 3 from 192.168, 3 from 172.16, 3 from 10, and some MAC addresses that go with it that said, hey, this MAC address is allowed to use that IP address, 192.168.0.2, and because there's no lease expiration, they can have it forever. They never have to give it up, but they dynamically learned it. So buried in here is the 10.3, or was it 2? Hover over PC8, 10.2.0.0.2. That's going to be the MAC address, BD4D, of PC8. There it is, on the far right-hand side, top right corner of that little rectangle, BD4D. So the router is keeping up with those leases. It is the one saying, hey, you wanted an IP address? Here is your response. It got a DHCP request. This one made a DHCP offer and said, hey, you can have this IP. Do you want it? The PC8 said, yep, I'll take it. Thanks. And you're locked in. Good to go. So all the PCs have IP addresses. No surprise. That's what we configured in the first lab, and it seems to be working, with the exception of the fact that some of these are acting really funky, and they've decided that they have somehow magically have their own DNS server that they shouldn't. It's a bug. Yeah, exactly. See, we did not issue this out, but it's still showing up on there. It's a bug in the software. I apologize for that stupidity. So, and again, this emulation software isn't perfect. It's a learning tool that has a few bugs. It's part of the game. I mentioned that in the first time we did this. I went into a lot more detail about what Cisco Packet Tracer is and how it works. I'm not specifically endorsing this particular version of software. We're not specifically endorsing this particular platform of network equipment. Juniper and all kinds of other companies out there make lots of Netgears and Linksys and you name it. MikroTik. I could come up with 1,000 names of manufacturers of routers and switches. We don't have a particular stance on them. It just so happens that this emulation software is easy to use. So I like to use it. It's convenient for me. It shows up well on the screen. They've got the cute little icons for routers and switches and PCs. So it's kind of convenient as a teaching tool. I use it all the time in my job with my team that works under me. It's just a very convenient tool. So definitely don't take this as an endorsement. It just happens to be the one we chose to use. So, and yeah, as you can see, it's not perfect. None of them are. They all have their own inherent flaws or bugs or limitations. It's the nature of the beast. So, all right, so we've taken note of the fact that from a DHCP management perspective, the router is the guy or gal giving out the IPs to anybody that requests an IP address. And it also gives out some ancillary information like your default gateway is this, your default gateway is this. And you'll notice that we have some excluded addresses. Anybody know why we have to exclude these IP addresses? We're not allowed to give them out as a DHCP lease, as a client lease. Any thoughts, any ideas? Feel free to unmute yourself and answer the question. I don't mind. It's much more fun when it's an interactive experience. Don't be shy. I know you know the answer to this. Why can't we give those IPs out to PCs? Why is that not allowed? Yeah, we don't want it to give it out, Jeremy. That's correct. But why? Why don't we want them to give that IP address out? Why can't that go to one of my PCs? I wonder if I have to say that I answered your question for you. Oh, there. It would cause a duplicate address. Yes, that's exactly right. Precisely right. What did we see when we typed show IP interface brief on this router? That IP is already taken. And this one's already taken. And this one's already taken. You can't have two with the same IP. That's the rule. Rule of IP routing is you can't duplicate, which is exactly why we never tell the internet, I have 10, I have 192, I have 172. We've all agreed in internet universe, we promise to never advertise those networks out to the universe because we're all using them. We're all duplicating that space internally and we're hiding that from the rest of the internet. So in this case, yeah, I have 10.0.0.1 here. I can't give it out in this lease. And you'll notice this network encompasses 10.0.0.1. So we've got to do that. Now, realistically, the router is actually smart enough to not do that. It'll detect the conflict and say, something's wrong here. Best practice is you exclude the addresses you know you never want to give out. It automatically excludes the network address 00. It automatically excludes the broadcast address .255. But the rest, you got to specifically tell it, hey, don't give this out. I'm using it for something else. If we had a printer plugged into this network somewhere that we always wanted to have a static IP because that's the best way to manage a printer, you specifically want to pull it out and exclude that address from being leased so you don't ever have that conflict. Good stuff. And thank you for answering, Jeremy. I appreciate that. So cool. It doesn't make the question go away, so I'm afraid I'll miss you. That's why I keep typing the same silly answer over and over again. Send privately. Send privately. Okay, good. I just don't want to miss any more question marks that pop up. I know Jessica's laughing her butt off right now. That's okay. I don't mind. Let's see. So we need to make sure they learn DNS. And despite the cheating that's happening here, all you little dirty rat cheater PCs that are supposed to not know this yet, let's figure out how to do that. So we have these pools that give out network information and they give out ancillary information like default router. No big surprise. There's probably a command buried in there somewhere that gives out DNS information. It's actually a lot of stuff. So if I say configure terminal, okay, I'm in global configuration mode. Now I want to configure the IP DHCP pool named, let's start with accounting. I believe that is case sensitive. Yeah, that is case sensitive. Now we're in DHCP config mode. Notice our prompt changed. Let's do question mark. What are all the things I can configure? I can configure a default router. Well, that's already done. Example up here for IT. I can configure a DNS server. Guess what? That's what we want to do. I can configure a domain name. I can configure the network, which we specified is the actual network that is the pool of addresses to give out. I can say undo some stuff with a no command, or I can specifically mention a DHCP option, option 43, option 202, 192. There's lots of different options out there. For us, let's just say, hey, if you're in the accounting pool and you're grabbing an address, you need to know that your DNS server is 68.188.0.2. And that's all you have to say. So, hey, anytime I lease an IP address in this pool accounting, which is specifically for the 192.168 network in this accounting department, make sure you tell them default router is .1 and DNS server is 168.188.0.2. And so let's do the same for the pool known as engineering. And I'm going to use my up arrow because I'm lazy, and network engineers are inherently lazy. And let's do the same for IT. And I'm going to use my up arrow. And so what we'll find is I'm going to type N to get out of global configuration mode, all configuration mode. And I'm going to type a show running configuration. And you'll notice now that the configuration, the indented section for all of our DHCP pools includes the DNS server. Now all of these PCs should learn it. Here's an interesting thing that happens. Let's see. PC 8 does not know DNS server. Still doesn't know it. Let's see here. ipconfig. Whoops, doesn't tell the whole story. /all. Very Windows-ish commands. DNS servers don't know it. Let's check it again. DNS servers don't know it. Why does it not have the DNS server? We just told the router to tell everybody that gets a lease, hey, here's your DNS server. Why doesn't it have it? Did we do something wrong, or did we forget a step? Jeremy's thought is, yeah, you got to renew the lease. Exactly. Once the PC learned it had an IP address, it doesn't go out looking for new information. And the router doesn't go out telling, hey, everybody, if you got an IP, also here's some stuff you need to know. It's got to actually request it. So I can unplug this port, I can reboot the PC, or I can even type in the PC's configuration on the command prompt, ipconfig /release. It says, okay, I give up all of my IP information. I no longer want it. And then I can type renew /renew. And it should take a bit, and you should get a response from the server. Server said, hey, oh, you want an IP? I already had one reserved for you, or not reserved for you anyway, but I remember the last one I gave you. I'm going to give you that again. Same subnet mask, same default gateway, but now we've learned DNS. So we know it's functioning the way it's supposed to. If we do it here on PC 5, despite the fact that it's not showing up the way we want, ipconfig /release and renew, we should in a moment get all our good information. It was probably .4 before, so it's .4 again. And we'll pick one in account. That's the switch. That doesn't do us any good. One in accounting. So let's do PC1. PC1. I know it's a bit repetitive, but it's one of those make you feel good because you checked every subnet kind of a thing. /release and renew. Give it a second. Boom. And we got all the information, including DNS. So we seem to have done step 3 successfully, and that's all it took was a simple DNS server command, a DHCP scope option that we added to each DHCP pool. All right, cool. Got that one, Send. Cool. All right. So we are nearly home free. The next step it says is, hey, you got to configure NAT on your router in order to allow the host on this private internal network access to the public internet. Well, let's test that theory because we've got a DNS server now. We've got a gateway. Each of our PCs has a default gateway. So you're telling me this isn't going to work? Let me just see. Can I ping my DNS server that I've learned about? Ping 68.188.0.2. Maybe it's ARP. Maybe ARP is why it's not working. No, definitely something's still not working. Yeah, it's not working. I'm going to cancel that with a Control-C. Let's try to trace route that same IP address and see if it tells us the story of how it goes. Okay, it goes to my gateway IP, which we know lives on router 1. So it goes from here, gets switched. You notice those switches don't show up in this trace. The next IP hop is up here at router 0, but then it dies after that. So it's trying to go out here and it's not making it back, or it's not getting out there. Reason is the internet world doesn't know anything about this 10 address. It's never coming back because we've never told the internet world there's 10 address exists here because we're not allowed to. Even if we tried to advertise it to the internet would say, no, I'm not taking that. I don't know anything about no stupid 10 dot. We agreed we're not going to talk about 10 dot. What happens in 10 dot stays in 10 dot. So we've got to figure out how to translate our source IP to a usable public IP so the traffic knows where to come back. And that's where that NAT, that network address translation comes in. So let us see how to configure that. Guess what? I didn't review before we did this. So it's going to be really ugly, me figuring it out with you. We're all learning today. I got to refresh my memory. So network address translation specifically refers to IP addresses. So we want to start with the IP keyword in our configuration command. And if we say IP, you can see the next possible command using my context-sensitive help, my little question mark, is, you can do route like we did earlier. You can do host. You can do all kinds of stuff. In this case, we want to do NAT. We specifically want to configure IP NAT stuff. Interesting. We have an IP NAT pool. Inside, outside, It looks like we're getting ahead of ourselves with NAT. We've got to, we got to have a pool of addresses. Actually, no, I'm sorry. We don't need to define a pool here because we're just going to use the one public IP on this interface. That's the only public IP we have. It's the only one they gave us. Remember in the instructions, you just get this one. So we don't even need a pool of addresses. We're just going to say, let's translate the inside source address. Remember, it's the source of the traffic that we need to translate because we can't take this IP out there with us. You're not allowed to take it outside. So let's translate our source address. Well, I do need a list. I'm a bum. Source list. We're going to have to create an access list. We got to specifically say what addresses are allowed to be translated to the 24.217.0.102 address that lives on that interface. 102, right? Hover over it. Yeah, 102. All right, let's back up. This is why you prep in advance. That's okay. This is how we learn. So let's create an IP access list. And we're going to create a standard one because we just need to identify the subnets that are allowed to be translated. And we're going to say it's list number 1 because I'm lazy. And that's all we have to type. IP access list, standard access list, not an extended access list with fancy extra stuff. And we'll call it list number 1. We could call it list Fred. We could call it anything we wanted. We're just going to call it 1. So now we're in standard named ACL configuration mode, or numbered ACL configuration. Yeah, that sounds right. Now we get to pick all kinds of stuff. So what we're going to do is we're going to permit traffic to be specifically natted or translated. Natted is the sloppy, shorthand, lazy way of saying it. We're going to specifically say these are the addresses that are allowed to be permitted or allowed to be translated. So we can permit, let's see, let's permit the 10.0.0.0 addresses. We need a inverse mask from our regular subnet mask. So if you recall, the subnet mask is /24 or 255.255.255.0. Well, for access list, you have to do kind of opposite day. So instead of 255.255.255.0, we've got to do 0.0.0.255. I'm not going to get into why you have to do it for ECLs and some network configuration commands for dynamic routing protocols. That's a deeper discussion for another day. Suffice it to say, we're still saying the same thing. Anything in the 10 network /24 in our cute little reverse notation or inverse notation is permitted. And that's all you say in a standard access list. It's permitted for something. We're going to say what that something is in just a moment. So let's allow the 10 dot network. Let's allow the 172.16.0.0, whoops, 0/24 network. And let's allow the, I'm lazy, 192.168/24 network. Those are all permitted. If you say nothing else, those are the only things permitted in an access list. An access list always ends with what's considered to be an implied or implicit deny. Anything that doesn't fit in that description, 10./24, 172.16/24, 192.68/24, is denied. We're not going to translate anything else. Only those are permitted. And if you recall, again, this is access list number 1. That's the name of it. We just called it 1. Now that we've done that, let's exit out of standard numbered ACL configuration mode, go back to global configuration mode, and go back to our IP NAT inside, whoops, source. Now we have a list describing the local addresses. Okay, cool, we can do this. We specifically didn't do static because there's, I don't know, 750 addresses that we'd have to map. We don't want to do that. So source list, what's the list of allowed local addresses that are allowed to be translated? Well, it's list number 1 that we created up here. So source list 1, I'm just using the question mark every time. That's how you remember how to work your way through it. And we're going to specify the one interface that has the one public IP that we're allowed to use. So let's say interface, pick one, anyone. Why? Fast Ethernet 0/1. That's our magical interface. Let's double check. Is that true? Yes, it is. I hovered over the green thingy so I can see that it's there. What we're saying in this really confusing, mixed up, scattered junk of a command is, hey, do a network address translation for an inside address that would be the source IP address in a packet, not the destination. Any of them that fit in list number 1 are allowed to be translated or natted, and translate that source address, change it to the IP address that lives on interface fast 0/1. That's a lot. I know that's a lot. If you're not confused by this, you're a very experienced engineer or you have a good sense of the concepts. Even some of my first tier engineers still scratch their head and go, wait, explain that to me again? If you need me to slow down or to draw it out, I may even draw it anyway, just for the sake of doing it. Please feel free to speak up. You're not going to hurt my feelings, and nobody on this call is going to laugh at you and call you stupid. There are no stupid questions. So now we've configured that global command that says, hey, translate any address that fits this list to this address that lives on that interface. So again, let's end out of here, do a show IP interface brief. That address on Fast Ethernet 1 is 24.217.0.102. Anybody here that wants to talk to the internet has to trade out its source IP address. For example, PC8 is 10.0.0.2. You got to trade it out for this IP address. That's what our NAT is doing. Trade it out. So let me go back to the drawing board here. I'm going to untop this so I can, you go away. So I can do this. Let me just doodle it real fast for my own sanity, if nothing else. We got an, that's not the bush, sorry. We've got an IP packet. So we're not paying attention to Ethernet frame. We're not paying attention to MAC addresses right now for the sake of this conversation. This is all layer 3 stuff. And the IP, excuse me, the IP packet has some payload like hi. And among other things, it has a source IP address and a destination IP address. If 10.0.0.2 wants to ping 68.188.0.2, It's going to travel through the switches and routers. It's going to arrive at this router. And this router is configured to do a network address translation that when it comes out of the router headed towards the internet, instead it's going to look like it came from 24.217.0.102 headed to 68.188.0.2. New source, same destination. I scribbled all over that. Shame on me. And guess what? The payload's still the same. It's still a hi. Hi. We're not actually done yet. Let's validate that. Where'd my router go? I have erased my router. Right there. Sorry. All right, so back to router 0. Let's put her back on top. Let's do, oh, no, I want to go to my PC8. Let's go to PC8. Let's try that. We now have it set to NAT. It should be NATing. So can we ping 68.188.0.2? Waiting, waiting, waiting. Timed out. Timed out. Nope, yep, as I suspected, it still doesn't work. There's something still not defined here. Anybody have any guesses as to what we might have missed? I thought we did everything. I mean, we said, hey, NAT these addresses, NAT all these spaces to this 24. Go ahead, Dylan.
Don't you need to set the out-facing interface to IP NAT outside?
Absolutely, that's exactly right. So good, I've got some folks that are experienced on this call. There's at least 2 of you that are experienced with this, so that's good. Yeah, you're absolutely right. We need to tell the router, hey, by the way, that NATing stuff we talked about, let me get rid of this again. Thank you all for being patient with me, those of you who have advanced knowledge of this. So we got 3 subnets that live off this router. Granted, they're kind of sharing one physical interface, but we have 3 subnets. And we've got this one out. So these would be all considered inside interfaces, and this would be considered outside. And like you said, Dylan, and Jeremy as well, we got to say, hey, by the way, with respect to NAT stuff, this interface, Fast Ethernet 0/1, I know my handwriting is illegible. It's an outside interface. We got to tell it that, otherwise it's not going to know what it's supposed to be doing. So let's go to configure terminal. Whoops, excuse me. I know I'm being silly with my constant clicking around. And we've got to go into interface configuration mode for Fast Ethernet 0/1 and say, hey, it's an IP command. You can see NAT in the list. IP NAT. What are our choices? Inside or outside? Is this an outside or inside interface? Well, this is an outside interface. Ah, sweet. Now we have done show IP NAT statistics. We have specifically said, hey, Fast Ethernet 0/1 is an outside interface. That means that this NAT rule we wrote is now active and alive for the sake of the outside interface back there. So for grins, why don't we go back to PC8 and try to ping? Let's see what happens. Ping 68.188.0.2. Nope, still not happening. What did we miss? What did we miss? I don't understand. We did the NAT. We created the list of addresses that are allowed to be NATed. We specifically created the NAT rule, the translation rule that says, hey, take any of these addresses that want to come through this interface and give them that IP. And then we even specifically said, hey, that interface is an outside facing interface. So why is it not working? Let's go here. Let's go to show IP NAT translations. Let's look at all the translations on this router. There's nothing there. It's not getting translated. Why is that? We told it what to do.
Do we still need to create a NAT pool?
Let's have a look. Show IP access lists and show run pipe include NAT. I think that's what I want to say. Let's see. Here's our list. We made the list and we specified, including PC8 subnet, that's allowed or permitted to be translated. It's permitted because we used a permit statement, and it is referenced, this list 1 is referenced in our NAT command. Hey, for this inside source address, if it matches any of this list, which PC8 does, then let's give it this command. Oh, and I did miss my overload command. I didn't mention that earlier. We'll talk about that in just a second. I apologize for that. I should not have missed that. Shame on me. And we said, hey, that's the outside interface. So why in Sam Hill is this not working? Let me go back to show IP NAT statistics. The hint is right there. See if you can spot it. I'm going to make my chat bigger so I don't miss any more chatty question things. Or questions, I mean. Anybody see it? We did forget a step. This may be a platform specific thing, and maybe not all devices by all manufacturers have this requirement. So it turns out, as you mentioned, we need to tell it, hey, this is the outside one. This is the one that is the internet. But Mr. 1841 does not assume what the inside interfaces are. You'll notice we haven't configured any inside interfaces, right? So if this is outside, then this must have something to do with inside. This fast Ethernet 0/0. So the question is, what do we configure to specify inside interface? I really want feedback on this one. If anybody knows what I should do, and it's okay to be wrong. I'd rather have your guess than nothing at all. We'll talk through it.
Can you say that again? I think I missed part of the question.
That's okay. So I identified, or I gave away the hint or answer that, hey, we specified an outside interface, but we haven't specified any of the inside interfaces. And it turns out this particular platform, this particular model of router and manufacturer requires that you tell it what the inside interface or interfaces are. So my question is, what should we, just as we did, where's it at? Just as we said, interface, let's do a show running config. It's easier that way. Just as we said, hey, where are you? Fast Ethernet 0/1 is an outside interface for the purpose of NAT. We need to say, hey, inside interfaces are these. So what would our inside interfaces or interface be? How would you do that? Again, you're allowed to guess. It's okay. If you get it wrong, we're not going to end the world because it's a lab environment. We won't break the whole internet. Go ahead, Dylan.
To your interface, so what is it there that goes towards the LAN 0/0?
Yeah, absolutely.
Go into that IP NAT inside.
Yep, so walk me through it real quick. Config T, right? Config T. What else do I need to type?
INT space F00.
F00 and hit enter.
Yep.
All right, and then what else?
IP space NAT space inside.
Yeah, inside. All right, so interface fast 00, the physical interface facing the south or facing all of our LAN. We're calling it an inside interface. I'm going to come out of here. I'm going to say show IP NAT statistics, and you'll notice that now I have an outside interface and I have an inside interface. Cool. So maybe that covers all the bases. Let's try it. PC8, can I ping something out there on the worldwide internet, on the interwebs? Pinging, pinging. I'm not feeling warm and fuzzy about it. I think we missed something. Anybody have any thoughts on what we could have done wrong? Because we made a tiny, slight error.
I was just going to reiterate what Jeremy already said. I thought you still had to make a NAT pool, and then you have to tell IP NAT inside source list.
Yeah, we have it. It's right here. We just did our show running config, and it's right there. It's already there.
No, your NAT pool, not your access list. IP NAT pool, name the NAT pool, and then the IP address.
I
and
follow.
then net map.
Okay, I follow you. No, so we could have done it that way, but for the sake of this particular function, especially this overload thing, we actually can just do it with an access list. We're good here. I follow you. What you guys are saying. I wasn't catching it at first. For the sake of this function, the access list itself is sufficient to be the pool. We're good there. And technically, it's really, the pool is only one address because it would have been the outside pool. But your logic makes sense what both of you are saying. I'm not disagreeing with you. It just turns out we don't need to do that here. Somebody else, Justin unmuted a second ago and I saw it, so you can't escape from me, Justin. What were you going to say? What was your suggestion?
I was going to say, did you ever renew release on that PC?
We did, and it shouldn't matter for the sake of NAT up here on the router, but that's a really good question. And we did. We certainly did. So we know everything we need to know. And because we're just trying to ping an IP address, it kind of doesn't matter. DHCP doesn't come into play here. So, but we do happen to have the new stuff, so we know that part worked. So here's the trick. Turns out fast Ethernet 0/0 is certainly the physical interface, and more specifically, it is the interface of all of our choices that handles untagged traffic. And that's really the key here. Get this fella out of the way. What we said when we said, hey, let's do a show running configuration again. When we said IPNet inside, we said any traffic that comes in through this interface that is untagged, this is a NAT or an inside interface. This is for the purpose of NATing, this is an inside interface. Well, is there really ever going to be IP traffic coming in this interface that is untagged?
So just do the command on all the sub interfaces, right?
That's exactly right. Exactly. All the traffic that's untagged coming into this router has nothing to do with IP routing. It's some control plane traffic between the router and the switch or switches, and that's about it. The only traffic that's ever going to come from PC8 or 5 or 2 or 1 or anything, it's going to be tagged either 10, 172, or 192. So those IP interfaces need the IP-specific command. So to do this right, to keep our configuration clean, if I could type, I'd be great at this job. I'm going to go back to fast Ethernet 0/0 and say no IP NAT inside because it's not an interface we're going to NAT on. You don't ever want to leave yourself open like that. That's basically exposing you. And let's go specifically to interface fast Ethernet 0/0.10. That sub interface, now that we're in sub interface configuration mode, must be IP NAT inside. Whoops. All right, let's test the theory before we configure the other two sub-ins in case I'm wrong, in case you guys are right and we still haven't configured this thing properly. So let's go back to PC8 and let's try to ping 68.188.0.2. And I mean as fast as we can type it, we're pinging successfully. That means we must have gone through this router, gotten added, hit our target out on the internet, and got a reply that got re-natted on the way back to come all the way back to PC8. So that's one of the functions of those inside and outside interfaces is the router is essentially keeping up with and show IPNet translations. It's keeping up with those translations so it knows where the return traffic is supposed to be going. If it didn't keep track of them, it wouldn't be able to, it wouldn't function because everybody's sharing 24.217.0.102. And that's really where the overload comes in. You also notice, by the way, there's 4 separate translations for all 4 pings instead of a single translation because each ICMP echo request and reply sequence or process, it's its own separate conversation. It's not a single TCP stream like if we were streaming video, or that's not a great example, some kind of web page transaction where we had multiple packets going back and forth, that would be a single translation. And we're going to prove that here in a second. But for ICMP, we actually have a separate flow for each ping. So, well, let's look at that. The only way this thing is able to keep them distinguished and separate is by after the colon, this port number. So the combination of an IP address and a port, whether TCP, UDP, or some other magic thing, is known as a socket. And essentially it uses that identifier. First it was 10.0.0.2:22, or port number 22, headed towards port number 22 on the destination. You notice it got translated our source. It didn't change the port, but it did change the source address. But the outside never changed. We didn't build a NAT to change the outside. We don't need to change the outside. So that's okay. And it did it 4 separate times. That's why we have 4 translations in there. And if we wait long enough, you notice now when I say show IP NAT translations, it does time out. It's not a forever thing. If it doesn't sense that the traffic is flowing, it eventually flushes them because it can't keep up with them forever and it needs to keep them separate. So the overload command that we forgot to put on there, but the router knew implicitly that we needed it, is because we've got about 750 possible source addresses in our show IP access lists. We've got about 750 possible addresses represented by these 3 statements, but only 1 possible outside address. So 750 inside, 1 possible outside. You can't, how do you share them? You say, hey, this is an overload scenario where we're going to have to pay attention to the source port number to keep the conversation separate. And so the ICMP is not a great example, but for TCP and UDP flows, the source port number is typically something what we call ephemeral ports, basically randomly selected above 1024, I think it is, all the way to 65,000, and I don't remember what. And it gets randomly selected. So we're playing the odds that they're never going to overlap, and it'll keep the conversation separate. And it works exceptionally well. So I think we confirmed that, yep, inside on the subint is the way to go. Let's do that for our other sub-interfaces. Config T, interface fast Ethernet 0/0.172, IP NAT inside, and .192. See how I use the up arrow because I'm lazy? All right, so if I say end show IP NAT statistics, I can see I have 3 different inside interfaces, 1 outside interface. I think we're there. I think we've nailed it. Let's just double check. We'll hit PC5. Can I ping 68.188. Whoops, too many 8s. That's 0.2. I sure as heck can. And PC2 is a good example. Let's try that one. Can I ping? Whoa, slow down, hot rod. Ping 68.188.0.2. And if you could type, you would be good at this job. There we go. All 3 subnets hitting the internet, getting a reply successfully. They're all getting natted. If we go to our router, we're going to see a nice long list of IP NAT translations. Oh, look at all that. Wow, look at that. And yeah, it didn't have any of the 10 dots because we didn't hit those. And yeah, that's interesting. There is a translation that is not one of our pings. That came from 192.168.0.2, which would be this PC, I think. No, this PC, I think. No, BZ2. That was specific to, destined for port number 53. Gee, I wonder why that is. And you'll notice it's above 1024, like I told you, for the source port. Oh, I wonder what that's about. Well, we'll leave that one aside for a second, although I know one of you knows the answer to it. And let's do this. Let's test the configuration, because we've done everything. We've done everything else on the list here, including that. Let's test configuration by successfully attempting to access www.abcplastics.com from at least 1 PC per lane. So let's grab PC8 again. Let's close the command prompt and go to the fancy schmancy web browser. By fancy, I mean it's not so fancy. I don't want to type www.abcplastics.com, hit enter, and boom, we got a web page with all the cute little links and everything. How cool is that? All right. Let's try from PC4. Desktop web browser, type www.abcplastics.com. I got a web page. Very cool. And just do PC1 for grins so we can say we did and satisfy the criteria. www.abcplastics.com, and I got a web page. Let's go back to HQ router and look at all of our translations. Man, it's blowing up in here. So it's keeping track of all of these requests. And in fact, what you'll notice is we have a whole bunch of UDP headed to port 53 on 68.188.0.2. I see Justin popped something in there. DNS uses 53 and 1023. We don't have any 1023s, but we definitely got some 53s. And then after these 53s, destined for port number 53 on, hey, what is that? It's a DNS server. Then we've got these 80s. Now, in the real world, you're not going to have the same destination address for the website. Turns out the DNS server is also the web server in our cute little lab. Probably should have done that differently so it's not so confusing. But 80 is specific to HTTP. This is web page web browsing port number. Headed towards this server, I want a reply back on, I'm shooting for your port 80. Are you a web server? If so, give me the web page I asked for. And you can see each of these devices getting the web page, served up to it. And all these are timed out probably by now. I've been talking so long. No, they're still in there. So we can actually see each of the flows, service flows, each of the translations for both the DNS request that had to happen because we tried to open a web page and for the actual web page coming through. So if we were to scan or Wireshark or put this in simulation mode, which this is capable of, we can look at all the cute little envelopes going back and forth to the internet and back for those conversations. And yeah, Justin, a random above 1023. So I was close. I was really close. It was not above 1024, it was 1023. So yeah, I think we have done everything. There was only one other thing I wanted to check, and it escapes me. Show IP access lists. And you'll notice now we're seeing all these matches on the ACL because we are successfully translating. Each of these represents a successful translation from one of our requests where we pinged or we attempt to do command. And thank you for reminding me, Justin. So the overload command specifically talks about I've got 750 addresses, but I've only got one that it can be translated to. Overload says, hey, you've got to pay attention to these for the translation. They must be unique to keep the conversation separate and clean. PCs are also doing a good job of keeping them separate and clean as well. In some cases, you'll notice that it actually changed the source port number because 1025 had already been used. This socket had already been used for 10.0.0.2's request. So when this guy sent a request, 192.168.0.4 sent a 1025 source port towards this destination address and port, he said, oh, wait, we got to change that because 1025 is already in use. And if I use it again, how am I going to know this response is for PC5 instead of PC8, as an example? So that's what the overload command is doing, is saying, hey, pay attention to all of that because everybody's having to share this IP address. Now, if we create the NAT pool that you guys talked about, we can absolutely create a pool of addresses and say, hey, this whole pool of addresses can be the new translated outside addresses. Oh, we've only got the one to work with, so creating a pool doesn't make sense. So that's why we just specified the outgoing interface as the new address, the outside address that we're going to translate to. So gets into a little more advanced NAT stuff that we don't need to cover here. But that's really the gist of this lab. This second play is we created all of this on the first pass, and now we bought us some internet. And we got to configure stuff to make the internet work. And we did. We configured, basically it was all on router 0. Everything else was already kind of set up and ready to go. And we just, again, show IP interface brief. We said, hey, this is a DHCP address, acquire address dynamically, which it did successfully. So the ISP kept their side of the bargain. We created show run. It's easier to do a show run. We added the DNS server to all the pools now that we had an actual working DNS server. Because you notice there's no servers in here. We didn't have one. And we decided to set the sub interfaces, the actual IP interfaces, as NAT inside interfaces, and the one facing the internet as our NAT outside interface. We created a rule, a NAT rule that says, hey, inside addresses, if their source matches this list, change their source address to be the IP address on this one interface. And yeah, there's a bunch here, so you're going to have to overload. Oh yeah, I forgot. We created our default route, which normally we would be getting dynamically from our internet service provider, but I added that, I believe, just because I wanted to add that concept in there and have to be aware of it. I'm pretty sure that's why I did that. And then you'll notice list 1 referenced in our NAT translation rule is defined as such. If your 10 dot address, you're permitted to be translated. If you're 172.16, you're permitted. If you're 192.168, you're permitted. If you're not any of those, there is an implicit deny everything else command here. In fact, it's not uncommon. Let's do that real quick before we quit for the day. If I say config T, access list 1, deny any address, it should add it to the bottom of the rule. Show run. Hopefully I'm not stupid and it didn't replace everything. Yep. So it's actually best practice to go ahead and throw the deny rule in there, because if you do show IP access lists, it'll actually log the denies too, which is kind of helpful for troubleshooting purposes if you ever have to do that. So there you go. Does anybody have any questions before we wrap for the day? We're kind of at that 2-hour mark, and I know it's 5 o'clock for most, if not everybody on the call. Anybody, any questions, any concerns, anything you think I didn't cover? Did I tell you anything wrong? And feel free, this is the time. I think silence is an implicit, I'm fine with it, so I think we're good. All right, everybody, I want to thank you for joining today. I want thank you, Justin. I appreciate the compliment. Thank you for your patience. I know I hit a couple of bugs on this. I know I did not review the NAT stuff like I should have, so we fumbled our way through it. That's what's great about context-sensitive help and an understanding of how this stuff works. So I appreciate all of you joining. Thank you so much. I can be reached at hunter.hunter@charter.com. If you have questions that are specific, or if you have questions that you wanted to talk about that you weren't comfortable talking about in front of the group, or you want to repeat something we went through or in greater detail, again, I can point you to good information, good sources. We can have a quick email chat or conversation. Any of that stuff, I'm comfortable doing it. Everything I've shared here is common industry knowledge. There's no state secrets or anything like that, so I'm happy to share anything we talked about. Thank you again so much. I appreciate it, and we will talk to all of you hopefully very soon. Hopefully we'll have part 3, very soon, so we can just keep jumping into these things. And again, this lab builds on the next one. The next lab builds on this one, I should say. And our network grows, and our capabilities and our features grow. So if you're able to attend, I would love to have you. Thank you very much for your feedback and your conversation, and have a great day.